Okay, you need to know the probability generating functions for all the distributions we've met so far. So we'll start with the binomial. There is some mention of proof on your specification. It's very vague. So we'll do sort of a little bit of proof work with specific examples with these as well. So binomial distribution, discrete random variable x, n number of trials, p probability of success, and you should be fine with this formula. We were looking at this when we did negative binomial as well. So the probability x equals x, n choose x, p to the x, q to the n minus x. And if I go into an example, it's probably the easiest way to do this. And so into here, we've got an archer hitting a bullseye probability 0.6. She fires 3 shots at the target. The random variable x represents the number of times she hits the bullseye. Find the probability generating function of x. I think these are in the formula book. I'm pretty sure they are, but we'll do them from first principles. So you've got that little bit of proof work in there as well. And so x is binomially distributed. N is 3. Probability of success or of hitting the bullseye is 0.6. And I'm going to set this up as a table so you can see what happens really clearly. So binomial distribution starts at 0, so she could hit the bullseye 0, 1, 2 or 3 times. And then we're doing probability x equals x. And so let me just chuck the formula up there in case we need it. P to the x, q to the n minus x. And so when x is 0, the probability of not getting any bullseyes is 0.4 cubed. The probability of getting 1 is 3 choose 1, which is 3, times 0.6 times 0.4 squared. The probability of getting 2, 3 choose 2, pop that one to the left a little bit, and then it'd be p squared and times 0.4, and then the probability of getting 3 bullseyes will be 0.6 cubed. So that's just plugging into the formulae. And so to turn that into a probability generating function for x, then we're looking at doing 0.4 cubed plus 3 times 0.6 times 0.4 squared times t plus 3 times 0.6 squared times 0.4 t squared, and then plus 0.6 cubed t cubed. So if you sort of lump the 0.6 and the t together, then you should be okay with this. I think this is the same as expanding 0.4 plus 0.6 t cubed using a binomial expansion. So taking first part to the highest power, power goes down by 1 each time. Power of the second part goes up by 1, so we've got 0.6t, 0.6t all squared, 0.6t all cubed, and the binomial coefficients are 1, 3, 3, 1. And that sort of pattern will work for any binomial distribution, and that will give you your probability generating function, which I'll pop back on the other board. So if x is binomially distributed, then the probability generating function for x is equal to 1 minus p plus pt to the power of n. And that's the bit that I'm pretty sure is in your formula book. I keep meaning to check these little nuances. I'm pretty sure it's in there. Can't remember my students ever having to memorise that. And if you look at that, oops, sorry, that formula there fits in with this result here. So p was 0.6, 1 minus p is 0.4, and then pt is 0.6t raised to the power of n. So you could do this with any distribution to create your probability, any binomial distribution to create your probability generating function for x.